Okay, so we have spent a lot of time in genetics talking about a lot of different organisms. So this is a good opportunity to go back to your 3.1 evidence-based argument tool and just review the different organisms and what we saw there. You have pea plants, you have mice, you have some geckos that we've spent some more time talking about. And think about what other kinds of questions might we still have as we compare these different organisms. With our geckos, what patterns did you notice? Go ahead and pause me while you do that. Okay, I'm hoping that you noticed that with all our different gecko crosses, all our different pea plant crosses, and all our different crosses with mice, we saw the same patterns over and over again. We saw one trait that showed up in that F1 generation, and in that F2 generation, we saw that 3-to-1 ratio. And now we're getting to a place where we could probably explain that 3-to-1 ratio. But what about other organisms? Let's take a moment and revisit our albino little girl, the one that has albino skin, but neither of her parents have it, but her grandma has albino skin. How likely is it that we're going to get this little girl from these parents? Could you represent this in a cross? Again, practicing your egg and sperm chart and practicing your Punnett square to see how that goes. Go ahead and try to do that on your own to see if we can explain how likely it is that we will get our albino little girl from those parents. All right, so if you have a mom and a dad that are both carriers, meaning they have just this recessive allele, they're hybrids, but they themselves are not albino. This mom could make a big A or a little a sperm, and this dad could make a big A or a little a sperm. Excuse me, the mom's going to make eggs. If you put that into a Punnett square, you're going to have a big A and a little a coming as possible gametes from the mom, and a big A and a little a as possible gametes from the dad. These come together, and that means they can either make a big A, big A, a big A, little a, a big A, little a, and a little a, little a. This little a is special. It's two recessive alleles. Only when you have two of these non-functional alleles are you going to have this albino child. This is why neither of the parents were albino, because they each only had one non-functional allele. So as I see that there are 4 possible combinations from these gametes, and out of those 4, only one of those 4 is considered albino, we're going to say we have a 1 out of 4 or a 25% chance of 2 parents that are not albino having an albino child. So this sort of summarizes where we're at coming up to this point. But I wonder if any of you asked about other organisms. Do our inheritance rules work all of the time? Well, we know so far that one allele can be dominant over another, and that is the trait that's going to be expressed in our heterozygote. We know that each parent gives half their genes to their offspring through meiosis, and we know genes from 2 parents are combined through fertilization. We are confident on those things. But I also want to remind you that the gametes come together randomly in fertilization. But notice here it says one allele can be dominant over another. Is that always going to be true? Do these inheritance rules always work? Well, let's make a prediction. Take a moment and look at these 2 chickens. We've got a red chicken and we've got a white chicken. Pause me as you think about what you think their offspring are going to look like. Okay, so now that you've made that prediction, I want you actually to try this out on Explore Learning Gizmos. Do something called chicken genetics. Drag and cross these two chickens and see what you get. Again, pause this video and come back to me once you've tried it. Please let us know if you are struggling to log in to Explore Learning Gizmos. Email us and we can help you with those passwords. Okay. So at this point, you probably got a result that looked like this. I imagine some of you had predicted we would get red chickens or white chickens, but instead, we didn't just get one trait, we got both at the same time. We got red and white chickens. This is different. This is different from our pea plants, from our mice, and from our leopard geckos. Okay, so that means something different is going on. We've figured out something called codominance. So on your big ideas packet, page 17, you can go ahead and write down codominance. That's when the hybrids or the heterozygotes show both traits at once. Now, how could we represent this in a cross? Well, in terms of picking letters, you can pick whatever you want. You can stick with the capital in your lowercase. Sometimes you use apostrophes. Sometimes we use different letters. It really doesn't matter. But for this example, I'm going to use capital R and capitals W's to show that being red and white, neither one of them is dominant. They are codominant. They're dominant at the same time. Okay, that means this white allele in a female chicken this female chicken who's white can only make white allele eggs. And this male parent can only make red allele sperm. And we bring them together in a Punnett square, we're going to get, again, this parent gives only W's, this parent gives only R's. Therefore, when they come together, you can get an RW, an RW, an RW, or an RW. That's the only thing we can get, and we see that in our Punnett square again. So now that we know how to model codominance using an egg sperm chart or a Punnett square, let's go ahead and try to do that and make a prediction for when you cross two hybrids. You can go ahead and do that on your Explore Learning Gizmo, and you can also make that prediction using an egg and a sperm chart and a Punnett square on your big ideas page 17. Pause me and return when you're ready. Okay, so if you made an egg and a sperm chart, you would realize if you took a hybrid, one of your red and white chickens, it would have an RW and an RW. And it could make either R eggs or W eggs. The male could make either an R sperm or a W sperm. And again, we could combine those in lots of different ways. The R and R can come together. The R and W can come together. Again, this R and W can come together, or this W and W can come together. That's exactly what's demonstrated with our Punnett square. An R and R can come together. An R and W can come together. An R and W can come together, or a W and a W. These are our possible offspring genotypes that we can come up with, knowing that these two charts, the egg and the sperm chart and the Punnett square, can both end up giving us the same information. They're just two representations of the same idea. All right, well, what does that look like when we start to talk about ratios and percentages? Well, if we talked about percentages, out of the 4 combinations, only one of them was red, RR. So that is 25%. 2 of the 4 were red and white. So that's 50%. And then 1 of the 4 is white, and that's 25%. If we were to write this out in a ratio, we would say we would have 1 red to 2 red and whites to 1 white. So go ahead and run it on the gizmo and see if our predictions are correct. I expect that you get some percentages that are pretty close to 25%, 50%, and 25%.